Hello, in this video I will give an overview of AWESAM and I will show you how to use the package. AWESAM is a Python package with tools to create seismovolcanic event catalogs from seismic data. This includes a tool to download seismic data, detect events and create catalogs. There are also two optional steps. Firstly, catalog consolidation. This allows the comparison of catalogs from two stations. In this way, non-volcanic disturbances are identified. Secondly, earthquake classification can be performed too. This, for example, is the final catalog for Stromboli in Italy, generated by AWESAM. In the following, we'll write some code to generate the catalogs. This code can be found in a Jupyter notebook. There are some installation instructions as well. Also see this publication. It contains detailed descriptions of all steps and algorithms. If something doesn't work as described, please open an issue on the GitHub page. All is linked in the description. Before I show you how to use AWESAM for any volcano, let's test it for Stromboli. We need to configure some important settings first. The data center, the seismic stations, the channels, and the sampling rate. Also the coordinates of the volcano. Then define the directory where the seismic data will be stored and where the final catalogs will be created. To begin, disable catalog consolidation and earthquake classification. We'll see later how these optional steps work. Alternatively, you can change the settings directly in this file. There, each parameter is explained in detail too. Now the seismic data can be downloaded with mass_download.multiprocessing download. We only need to define the start and end date. For optimal performance, the download will utilize multiprocessing. Sometimes this leads to error messages not being displayed. In case something doesn't seem to work, add use multiprocessing equals false as an additional argument. When the download is ready, we can start the pipeline with catalog pipeline.multiprocessing pipeline. The final catalog will be stored as a CSV file. To be able to find it again, give it a nice name. That's it. Now the final catalogs are computed. This will take a few minutes. Again, if something does not work, turn off multiprocessing. Next, we can have a look at the catalog by reading the CSV file. How nice! Another way to visualize the catalog is with tests.testCatalog. This generates the following plot. The crosses indicate the detected events. However, if the eruptive behavior is different, this might not look that way for other volcanoes. In that case, we can vary the following four parameters. To show what these parameters are doing, we have to explain how AWESAM detects events. It is based on the adaptive max filter algorithm. In this algorithm, a window moves across the data and outputs the maximum value in each window. What makes this algorithm special is the variable window size. For example, the kernel size automatically increases for large events. The first important parameter, threshold window size, controls how quickly the adaptive filter size changes. It should be longer than the average event duration, but also not too large. Secondly, the kernel factor controls the average size of the max filter kernel. While applying the adaptive max filter, the data is also downsampled. This has no real influence on the result, but it improves the performance significantly. So we should increase the value if events are rare. The last important parameter is the threshold factor. This controls the minimum relative amplitude for detected events. Usually after changing one of these parameters, we would have to rerun the pipeline. But there's also a way to get instant feedback on the effects of these parameters. Use tests.testEventDet to create this plot. Okay, these were the most important components of AWESAM. In the following 2 sections, I'll explain 2 optional steps to get more information about each event. If 2 stations are available, catalog consolidation can be used to compare and combine 2 catalogs. In this way, non-volcanic disturbances can be identified. First, enable it. Then rerun the catalog pipeline. The new catalog has an additional column representing the probability that each event is volcanic. This probability is based on the distance of events in the time amplitude domain. It is computed with the following equation. To customize the result, change the parameter default metric. In many cases, it is useful to know whether an event is volcanic or if it is an earthquake, especially for large events. The earthquake classification algorithm attempts to estimate the arrival time and amplitude of earthquakes at the volcano. This is estimated from an official catalog. To use it, you have to download a regional earthquake catalog, for example the ISC catalog. It must contain the time, location, magnitude and depth of each earthquake. Store this catalog as a CSV file per year and change the setting earthquake catalog directory accordingly. Now set use earthquake classification to true and rerun the pipeline. The resulting catalog has yet another column called earthquake probability. See the settings in earthquake classification for details about the configuration. Here it is, the final catalog, ready for further analysis. How awesome!